The idea that the universe is expanding originated with the astronomer Edwin P. Hubble. Consider galaxies that are located at various distances and directions from Earth. Hubble found that light reaching the Earth from these distant galaxies is Doppler shifted toward greater wavelengths, that is, toward the red end of the visible spectrum. This type of Doppler shift results when the observer and the source of the light are moving away from each other. The speed at which a galaxy is receding from the Earth can be determined from the measured Doppler shift in wavelength. Hubble found that a galaxy located at a distance d from the Earth recedes from the Earth at a speed v, given by what is now known as Hubble's law, v equals h times d, where h is a constant known as the Hubble parameter and is equal to 0.022 meters per second times light year. In other words, the recession speed is proportional to the distance d, so that more distant galaxies are moving away from the Earth at greater speeds. Hubble's picture of an expanding universe does not mean that the Earth is at the center of the expansion. In fact, there is no literal center. Imagine a loaf of raisin bread expanding as it bakes. Each raisin moves away from every other raisin without any single one acting as a center for the expansion. Galaxies in the universe behave in a similar fashion. Observers in other galaxies would see distant galaxies moving away just as we do. Not only is the universe expanding, it is doing so at an accelerated rate according to recent astronomical measurements of the brightness of supernovas or exploding stars. To account for the accelerated rate, astronomers have postulated that dark energy pervades the universe. The normal gravitational force between galaxies slows the rate at which they are moving away from each other. The dark energy gives rise to a force that counteracts gravity and pushes galaxies apart. As yet, little is known about dark energy. Experimental measurements by astronomers indicate that an approximate value for the Hubble parameter is 0.022 meters per second times light year. This value is believed to be accurate to within 10%. Scientists are very interested in obtaining an accurate value for h because it can be related to an age for the universe, as we now show. Consider a galaxy currently located at a distance d from the Earth. According to Hubble's law, this galaxy is moving away from us at a speed of v equals h times d. At an earlier time, therefore, this galaxy must have been much closer. We can imagine, in fact, that in the remote past, the separation distance was relatively small, essentially zero, and that the universe originated at such a time. To estimate the age of the universe, we calculate the time it has taken the galaxy to recede to its present position. For this purpose, time is simply distance divided by speed, or t universe equals d divided by v, which equals d divided by h times d. The d's cancel, and we're left with 1 divided by h. Therefore, t universe equals 1 divided by 0.022 meters per second times light year. Converting light years to years, we have t universe equals 4.3 times 10 to the 17 seconds, which equals 1.4 times 10 to the 10 years. So, according to this calculation, the universe is about 14 billion years old. The idea that our galaxy and other galaxies in the universe were very close together at some earlier time lies at the heart of the Big Bang theory. This theory postulates that the universe had a definite beginning in a cataclysmic event, sometimes called the primordial fireball. Dramatic evidence supporting this theory was discovered in 1965 by Penzias and Wilson. Using a radio telescope, they discovered that the Earth is being bathed in weak electromagnetic waves in the microwave region of the spectrum. They observed that the intensity of these waves is the same, no matter where in the sky they pointed their telescope, and concluded that the waves originated outside of our galaxy. This microwave background radiation, as it's called, represents radiation left over from the Big Bang, and is a kind of cosmic afterglow. Subsequent measurements have confirmed the research of Penzias and Wilson and have shown that the microwave radiation is consistent with a perfect blackbody radiating at a temperature of 2.7 Kelvin, in agreement with theoretical analysis of the Big Bang. In 1978, Penzias and Wilson received a Nobel Prize for their discovery. Based on the recent experimental and theoretical research in particle physics, scientists have proposed an evolutionary sequence of events following the Big Bang. This sequence is known as the standard cosmological model for the evolution of the universe. Immediately following the Big Bang, the three fundamental forces, the gravitational force, the strong nuclear force, and the electroweak force, all behaved as a single unified force. During this initial period, the temperature of the universe was incredibly high, about 10 to the 32 Kelvin. Very quickly, in about 10 to the negative 43 seconds, the gravitational force took on a separate identity all its own, as we see here. Meanwhile, the strong nuclear force and the electroweak force continue to act as a single force, which is sometimes referred to as the GUT or GUT force. GUT stands for the Grand Unified Theory that presumably would explain such a force. Slightly later, at about 10 to the negative 35 seconds after the Big Bang, the Grand Unified Theory force separated into the strong nuclear force and the electroweak force, the universe expanding and cooling somewhat to a temperature of roughly 10 to the 28 Kelvin. From this point on, the strong nuclear force behaved as we know it today, while the electroweak force maintained its identity. In this scenario, note that the weak nuclear force and the electromagnetic force have not yet manifested themselves as separate entities. The disappearance of the electroweak force and the appearance of the weak nuclear force and the electromagnetic force eventually occurred at approximately 10 to the negative 10 seconds after the Big Bang, when the temperature of the expanding universe had cooled to about 10 to the 15 Kelvin. From the Big Bang up until the strong nuclear force separated from the Grand Unified Theory force at a time of 10 to the negative 35 seconds, all particles of matter were similar and there was no distinction between quarks and leptons. After this time, quarks and leptons became distinguishable. Eventually, the quarks and antiquarks formed hadrons, such as protons and neutrons and their antiparticles. By a time of 10 to the negative 4 seconds after the Big Bang, however, the temperature had cooled to approximately 10 to the 12 Kelvin, and the hadrons had mostly disappeared. Protons and neutrons survived only as a very small fraction of the total number of particles, the majority of which were leptons such as electrons, positrons, and neutrinos. Like most of the hadrons before them, most of the electrons and positrons eventually disappeared. However, they did leave behind a relatively small number of electrons to join the small number of protons and neutrons at a time of about 180 seconds, or 3 minutes, following the Big Bang. At this time, the temperature of the expanding universe had decreased to about 10 to the power 9 Kelvin, and small nuclei such as that of helium began forming. Later, when the universe was about 10 to the 13 seconds, or 500,000 years old, and the temperature had dropped to near 3,000 Kelvin, hydrogen and helium atoms began forming. As the temperature decreased further, stars and galaxies formed, and today, about 14 billion years after the Big Bang, we find a temperature of 2.7 Kelvin characterizing the cosmic background radiation of the universe.